I've been playing chess for a while now. It's a good game. I love playing it, I love watching it. But I have a teeny tiny problem with it. Why is this game so hard? How am I supposed to calculate a checkmate in 100 moves that a boy younger than me calculated in seconds? And why is that a draw? Anyways, I might not know chess, but I know programming a little bit. So to save myself, I'll be creating a chessbot in this video. To create a chess AI, I first needed a working chess game. Creating a chess game can be very tricky, and since in this project my main focus would be to create a chess AI, I will avoid creating the whole chess game from scratch. Instead, I would be using the chess library in Python to implement all the rules of the chess in the game, and using Pygame to create the GUI of the game. The chess library works on the FEN or the Forsyth Edwards notation. This is a standard notation used to describe a particular board position of a chess game, and using this, I can generate and capture different board positions for evaluation. From FEN, the chess library also uses a series of characters to describe the board state, and using this, I can generate the board position in Pygame. Each time you make a move, the board state updates. Also, the library provides us with legal moves, so the allowed moves can also be shown. And here is the chess game in action. Well, till now the process seems pretty straightforward, but in reality, the hardest part about creating a chess bot is to make a running error-free chess game. Because chess is such a complicated game with astronomically high combinations. It results in a lot of bugs and errors and edge cases to check that makes the playtesting process slow and painful. But anyways, the hard part is done, and now it's time for the fun part. To create a chess bot, we first need a function to evaluate the chess positions to compare which position is better and which move was used for it. As easy as it seems, creating an eval function may vary from person to person and position to position. For now, I have created the most basic eval function which compares the position based on the material of each player. Each piece is given a certain point, and the eval function will traverse through all the pieces on the board and calculate the total material score of both sides and return the difference. If the function returns a positive value, that means that bot has a material advantage, and vice versa for a negative value. Later we need to update our function, but for now it's a good starting point. Jumping into the algorithms, I would start with the min-max algorithm. This is a decision-making algorithm of game theory used in many strategic games like chess, tic-tac-toe, and other zero-sum games. Min-max works by evaluating all the possible moves of both sides till a certain depth is reached and backtracks to find the best move by minimizing and maximizing alternatively for each player. Here is how it works. Let the white dots represent the moves played by the bot and the black dot represent the other player's move. Each dot shows the move chosen by any side. In the min-max algorithm, the bot searches for all the possible moves till a certain depth or till the game ends. Here the depth is 3. After reaching the end node, it uses the eval function for the evaluation of the last board position. Let here the evaluations are -1 and 3, since it is the white dot or the bot's choice, so to maximize, the move with eval 3 is chosen. Similarly for the other side, 8 is chosen. Now it's the black dot or the other player's turn, so considering it plays the best move, the score should be minimized, so 3 is chosen. And similarly, the rest of the evaluations are made, and the final evaluation is 3. So out of the 2 moves the bot has, the left move is the better one to play, and so it plays it. To implement the algorithm, I created a recursive function with the base case a certain maximum depth, or if the game ends somehow. In each recursive call, the code calculates a certain move outcome, alternatively maximizing if it was made by the bot and minimizing if it was made by the other player, and then returning the best move. Here is the bot playing using the min-max algorithm with depth 3. Although the min-max algorithm works fine, with increasing depths, the number of positions to be evaluated increases exponentially, and with that, it becomes slower and slower for the bot to calculate the final move. To improve this, we can change our min-max algorithm by using alpha-beta pruning. Since we are considering that each side makes the best moves, we know that one side is trying to maximize and the other is trying to minimize the evaluation. Using this knowledge, we can prune some of our calculations. Taking the same example, the starting calculations are same as we have nothing to prune. But in this state, one of the choices of black or the minimizer dot is 1. So there are 2 cases now. First, the other side gives black a choice greater than 1. In that case, it will choose 1 to minimize. Second, the other side gives black a choice less than 1. In that case, that choice is selected to minimize. So no matter what choice black makes, the eval is going to be less than equal to 1. But on the other side, the choice for white or the maximizer is 3. So 3 is greater than anything 1 or less. So ultimately the left move is chosen no matter what black plays. So now we can prune this branch and we need not calculate the evaluations for that, which saves time and computation. In the min-max function, depending on the bot or the other player alternatively, the algorithm skips the min or the max value. Remember, alpha beta pruning is order dependent, and in cases where outcomes are in worst to best order, it does not improve the performance. Till now, we are using the material advantage as our basis of evaluating and comparing different positions. But in chess, not only the amount of pieces, but also their positioning matters. Now, evaluating the strategic position of pieces are not as straightforward as the material advantage. But there are some basic rules that in general sense helps to build a better positioning of a piece and hence results in an advantage over the other player. Using the material advantage, the bot evaluates all the position equal until the first capture is made. So you can basically develop all your attack before the bot and he won't be able to do anything about it. To avoid all these problems, we can increase and decrease the value of a piece depending on its position. Again, this is quite relative to the game state, but there are general places where a piece is better than others. For example, a pawn towards the center of the board has higher value than the one in the back corners. Knights on the edges are obviously bad placed and hence loses its value. King is better off at the back of the board rather than the center unless it is an endgame. I have implemented this using a different position matrix for each piece type, and according to the current position and color of the piece, the value of the piece changes, resulting in change in overall score of a position, and hence forces the bot to make strategic moves, like quickly capturing the center, developing pieces, and castling as soon as possible. The bot is right now winning against 1000 to 1200 elo bots on chess.com and is working pretty well for the amount of algorithms used in it. But there are a lot of things that can be improved with the bot. Things our bot needs work on are king safety, sacrifices, opening move, end games, repetition, stalemates, and much more. Also till now, I'm just using the algorithms for the bot. Next, we can use some strategies or book moves or machine learning even to make our bot much better. But that would all be explored in the next parts of the video. Finally, here are the matches our bot played with some of the other bots out there.
1, 2 Polizei, 3, 4 Grenadier, 5, 6 alte Keks, 7, 8 gute Nacht. 1, 2 Polizei, 3, 4 Grenadier, 5, 6 alte Keks, 7, 8 gute Nacht. 1, 2 Polizei, 3, 4 Grenadier, 5, 6 alte Keks, 7, 8 gute Nacht. 1, 2 Polizei, 3, 4 Grenadier, 5, 6 alte Keks, 7, 8 gute Nacht. Polizei, 3, 4 Grenadier, 5, 6 alte Keks, 7, 8 gute Nacht. 1, 2 Polizei, 3, 4 Grenadier, 5, 6 alte Keks, 7, 8 gute Nacht. 1, 2 Polizei, 3, 4 Grenadier, 5, 6 alte Keks, 7, 8 gute Nacht.
Thanks for watching the first part. I'll continue to add improvements to the bot and will keep you posted on the upcoming parts. The chess bot till now is available on GitHub. The link is in the description, you can try it out. Also, recently I created a programming language and posted a devlog about it. To watch it, click on this video. And that's it for today. We'll see you in the next video. Till then, goodbye.